Okay. Skill number two, we're still talking about direct variation. And so we used proportions to sort of set these problems up. That's sort of option one. That's always going to work. So to a certain extent, if that makes sense to you and you feel like you don't want to mess with a good thing, um, I, I guess I would never tell you to skip one of my videos, my precious videos. I guess kind of you could skip it technically. So this is just an alternate method to solve these direct variation problems. It is related to what we're going to do in the third video, which is the joint variation setups. So it's, maybe don't skip it. Don't skip it. Probably don't skip it. But don't get don't feel like you need to use this versus the proportions. You can sort of always use the proportions. I may be making a big deal about this only because I kind of prefer the proportions. That's usually what I would use if I was doing this on my own. But this method works too. And the idea here is you're going to use what we call a constant of variation. So this is literally the same example from above, right? So in the last video we did example 7.1, where we were talking about the sort of engine horsepower versus the number of cylinders. So this is literally the exact same problem, but we're going to try to solve it using a little bit of a different technique. So recall from the last video, hopefully 10 minutes ago in your watching. So a four-cylinder engine produces 100 horsepower, assuming the horsepower varies directly, right? So an increase in the horsepower is going to be connected to an increase in the number of cylinders and vice versa. What is the power of a 10-cylinder engine? So solve using a constant of variation. So the basic idea here, right, is the other way you can think of this relationship is, in this case, we're trying to solve for the horsepower, right? What is that power? So the idea here is that horsepower is some constant, some value C, times the number of cylinders. And that, in theory, is some consistent value, right? A constant value, literally. So an unchanging value. So there's essentially, in some sense, what it turns out being, it's kind of like a unit rate in some sense that connects our horsepower and the number of cylinders. The values here, if we start to sort of sub them in, right? And sort of rearrange this, if you actually sort of solve for C, right? You divide by the number of cylinders here. What you get is this C value is the horsepower divided by the number of cylinders. And then if we sub the numbers in, that's 100 divided by 4, right? 100 horsepower for 4 cylinders. Literally what we're doing is we're essentially finding a unit rate. So this is 25 horsepower per cylinder, right? Which, if you were probably starting this question, you might have even sort of said that to yourself when we did the last example, right? Okay, so it doesn't take a particular brain genius to see that if I have a 4-cylinder engine that gives me 100 horsepower, that's 25 horsepower per cylinder, and then I can sort of just multiply by 25 by however many cylinders I have. That's exactly the concept here, right? So the constant here is 25 horsepower per cylinder, horsepower per cylinder, horses power per cylinder. And so then solving this, right, in sort of a second situation, you're saying, okay, well, so then what's the horsepower going to be in situation number 2? Well, all you have to do is say 25, right, horsepower per cylinder, this constant, times the number of cylinders. So in this case, if I do a new situation where now I have a 10-cylinder engine, right, this is my sort of engine number 2, I know I get 25 horsepower worth of power for every individual cylinder. So it's just a matter of saying, well, 25 horsepower per cylinder times the number of cylinders, 25 times 10, gets me to my 250, right? Easy as that. Is this better or worse? It's neither. It just is different. It's just a different way of thinking about it. So I want to do another one from the exercises, and I want to use this setup instead. Again, proportions work always for direct variation, so you can use it and stick with it. You don't need to, if it's sort of not broke, why try to fix it? So you can always use the proportions, but this works too, so just as good. We're actually going to jump to number 11. Number 7 is a joint variation one, so we're going to cover that in video number 3. So ignore that. Jump to number 11. So this is a braking force one. The braking force in a car is directly proportional to the force applied to the pedal, right? We sort of said this briefly in the first video. The harder you press the pedal, the harder the brakes, right, will sort of press on the wheel. So when 40 pounds of force is applied to the pedal, the braking force, right, at the wheel is 1,670 pounds. So if the braking force is 1,450, right, that is at the wheel, how much force is being applied to the pedal? Let's run through it. So I've got it here. I've sort of copied over our information. So force at the pedal, right? Pedal 1 was sort of 40 pounds, and then at the wheel we had 1,670. We're trying to find the force in the second situation, force at the pedal 2, when the force at the wheel in the situation is 1,450 pounds. So the move here to set this up, you want to sort of set up just a quick equation based on what you're trying to solve for. You can kind of find this constant one of two ways, honestly. So if we're trying to find the value at the pedal, what I'd like is an equation where it's the pedal is equal to some constant times the force at the wheel, right? So the force at the pedal is some constant times the force at the wheel. Then if I sort of sub in my values, this was what? So from situation number 1, this is 40 pounds equals some constant times 1,670. So what's going to happen here is I'll divide by 1,670. I'm trying to solve for the constant. So this C value, 40 divided by 1,670. So this is sort of a small decimal. We'll call this 0.024, right? 2395. 0.24. So the constant here, right, in the last example was 25, right? And that was sort of horsepower per cylinder. You know, what would be my kind of makeshift units here, right? Well, this is sort of the pedal divided by the wheel. So what this is this is sort of pounds of force at the pedal per pound of force at the wheel. So this is, my constant is 0.024 pounds at the pedal per pounds at the wheel, right? So I sort of need 0.024 pounds of force on the brake pedal to get 1 pound of force down at the wheel. The idea, of course, in a car is that you're sort of multiplying. You're getting more force at the wheel than you get at the pedal. That's sort of the whole idea, right? We're not using the Fred Flintstone sort of brake model where we just slam our feet into the ground. That would just sort of be slamming force. Feet force is braking force. It's like a one-to-one relationship. We've made a few advances since the Stone Age, and now we have hydraulics. I want to say, I think it's hydraulics are a part of brakes. You guys can tell me in class or in the comments, I guess, what is brakes? How do brakes? Maybe that'll be our discussion question for today. In any event, so we have 0.024 pounds of force at the pedal per every sort of pound of force at the wheel. This is all a very sort of just long way to explain why this number is much smaller than the one that we had before. It all depends on the problem, right? What you're trying to solve for. So in this case, for our situation number 2, right? So my pedal force is going to be constant times wheel. So that's 0.024 times my wheel force, right? For wheel number 2 is 1,450. Let's see what we get here. I'm gonna space a little bit. 0.024, right, times 1,450, 34.8. Now this makes sense. It should be less force. relative to what we started with, meaning both, right, we sort of decreased how much force we were putting on the wheel, right, 1670 down to 1450, so we should expect to drop from 40 sort of proportionately down as well. So using this constant, this works. If you want, you can also do this with a proportion. Again, either of these techniques is fine. It's just a matter of sort of what kind of makes the most sense to you, really. It's sort of a choose your own adventure thing. So take your pick, either works. So go with what you like.